This is IBM Museum. In this video, I'm going to just be in front of the camera screen here on the webcam from my recording computer, just to go over one of the routines I've generated. I've had to give that quite a bit of an update based on what I've learned just in the last few days. And this is a routine. I'll get it up a little bit bigger on screen here in a moment and go through it line by line, give some explanation for it. But this is a routine to go through and check in software that it is a microchannel computer. And that's handy in some cases, in some programs, especially like the system information tool redesign that I'm doing, for going through and detecting, that it is a microchannel, and typically that means an IBM PS2 computer. Can be other brands, can be other in other series of the IBM lines, even some of the PC servers and things like that having a microchannel, or even a mixed bus in this case. So let me go through and just rearrange the screen, get the listing up, and start explaining things. Okay, and here's just a kind of a capture from the web page. I'll link in. I'll go through and move this. This is actually a text base, or just an image I move around, and I'll link in the web page that I'm referring to for this routine, for the CheckMCA or Check Microchannel Architecture, and also the interrupts page, where I get make the system call in software to get that information identified from the system. It reports on what's there. And we'll learn in some cases there is at least one system that misreports that, so we have to kind of account for that. And that's one of the changes I've made recently, and based on some previous videos that I did on the Model 50Z, and that covers also the PS2 Model 50 and the Model 60. There's some details with those being the 286 based microchannel systems. And IBM, I believe, I can't think of any other model microchannel system out there that used the microchannel bus, 286, CPU based. Even the development machine called the Delmarva machine by Chet Heath at IBM was 286 based initially. And I have a suspicion, I've never seen an image of that system. I'd love to see it. I'm sure that there'd be others that would love to see it, for that being kind of the initial microchannel system. I have my suspicions of what that kind of looks like. And in regards to the systems I'll talk about here. But here's the start of the routine. I just give that comment header up above, and I'm using semicolons, and I probably need to go through and update the comments I've done below in the listing with that semicolon as well. And this is basically assembly code, that a semicolon means that everything following that is a comment for that line. But I give an explanation at the top of the routine. The CheckMCA assembly routine. This routine checks whether the system has a microchannel, MCA meaning microchannel architecture bus. Entry means that there's not really any registers or values saved away as you enter the routine. On exit from the routine, the carry flag is clear if it's a microchannel bus, and the AL register has the number of microchannel slots that the machine is reporting in there. We have to do a little bit of finagling in one instance that I'll show in the code, but for that number of microchannel slots. But then the carry flag is set if it's not a microchannel bus and the AL register is empty, equals 0. So going through and moving this text up so we can go through and kind of have that on the screen. And I'll go through and I'll bring up the interrupt call. Okay. And like I say, I'll provide a link to where I have this online, where I have this information compiled online. And and we'll get to where we can interact with it. Okay, so this is interrupt 15 hex function C0 hex. And by the same way, it has the registers that call. I've got links, jump links to that to go to the points in the page. You can jump, and that effectively scrolls down further. But this is an interrupt call that makes the system report, and you put the value of C0 hex in that AH register, the high side of the AX register, and then you call interrupt 15 hex. And for the return registers, it talks about if the call's unsupported. You'll see that on early models of like the IBM PC or XT may not support all the full values of this call. I think it's the original PC doesn't do the support this call of what its configuration is or showing. And then if the call is supported, it actually provides a table of data that's pointed at with the ES or extra segment register and the BX register. That's a pointer to a table of where that information is going to be held for running basically checks on it to kind of decode that. Let's scroll through. And this is the table showing. And there's initially a word that shows the number of bytes that are following for that size of that table. Because as IBM filled out that table with later models, they added more flags within those so-called feature bytes that identified new things, new features that they were adding into the systems. And IBM established, I've referred to sometimes before some of the sequences when I've talked about the CPU level, the machines and things like that. They used a fairly common, or an easy to decode, what they called the BIOS model and the BIOS submodel of the computers. And it makes that kind of fall into place quite a bit. The BIOS model is very dependent upon what CPU that the system came with, and IBM quickly kind of got into where they weren't updating it at some point because they, as I show in the chart, for that first byte of information, once we get to this from the size of the table, is the model, the BIOS model, and that has particular encoding of the unit had a 386SX or higher CPU in it, and I've referred to that in previous videos, and I give little examples of that, being the MUL 70, MUL 80. There's some values in there like that F9 hex value that only covers the PC convertible. And it's even how the PC convertible actually has an 80C88. It's a CMOS based, square little chip of the 8088 CPU family. And it's the only PC that really has that form factor of the CPU. That you know that CMOS-based CPU was designed for suspend conditions and things like that the PC convertible had, and so that's the reason that it's kind of unique in this case and only has that particular value of the BIOS model cover that system. You have the FA of the 8086 based systems. IBM treating those different from the 8088 based systems of the earlier IBM PC, PCXT. And those FA hex models are the MUL25 and MUL30. Those initial versions, they had later units that were based on later CPUs. But the initial models had an 8086 CPU. And for just the bit of trivia, that 8086 CPU came out in 1976. I mean, it was slower, only designed for just a couple megahertz. But that's when that CPU came out and basically had all the features that the MUL25 and MUL30 used on those systems. Intel didn't add any really, other than increasing the speed and getting rid of maybe some bugs that were there. There were some bugs in the 8088 CPU that Intel had to get rid of for the later MULs. But and then you have the FB, the FC that we'll get into for the FC hex for the 286 based systems, and that includes the earlier PC series of the IBM PCAT. They had the XT286, even though it was called the PCXT. They had that 286 following to show that it was based on the 286 CPU, as well as, there's MUL25 286s and MUL32 286s that also had that. So they would have that FC hex being the identifier for the BIOS MUL. And that also incorporates the MUL50, MUL60, as identified there, the MUL30 286. There'll be one unit that we'll talk about here later on that has a 286 based CPU that we have to kind of encounter with that. Just like we have to treat that a little bit differently, just like the MUL50 and 50Z and MUL60. So there's the FD, which is the PC Junior, being 8088 based. FE hex, FF hex, and we don't really look at some of those 8086 or 8088 base when we want to determine the microchannel system, and there wasn't any microchannel MULs that were based on those earlier 8086 or 8088 CPUs. So following that model, BIOS MUL byte, we have the submodel, BIOS submodel. And IBM did things within that. I even provide the examples that we'll see later on of when the BIOS MUL was FC, meaning it's based on the 286, then IBM stepped through those for the systems that were based on the 286 CPU to be the MUL50, and also the 50Z being a BIOS submodel of 04. The model um, the submodel of the MUL60 being 05 hex. So they stepped through just based on subsequent versions that use that CPU for breaking out the submodels. And for some of the CPUs, they got rather involved. I mean, longer list, since those CPUs covered a lot of the range of models. Like the F8 BIOS model encoding was the 386SX or above, meaning 386SX, 386DX, 486SX, 486DX, 486DX2, 486DX4, Pentium level. They went through and they kept that BIOS model just as F8 to everything that was 386SX or above. And I've explained that before on prior videos. We go through from there to the BIOS, the BIOS revision. And IBM had the convention of that first version of the BIOS was 00. And if they later on had they fixed bugs in the BIOS or released the BIOS again, the next or the second version of the BIOS was 01, 02. It just followed sequentially as they went through and released things. Now, that BIOS revision, there's some qualifiers in there as well. I mean, they could have models that they released in different regions that had the same BIOS revision that were ultimately a little bit different. Normally, IBM attached a date to that release of that BIOS revision that was also in the ROM, where you could look at what that date was for that revision. And that date is also important to note too, because there are, in particular, the PS2s. There are some models of PS2s that they were up to a BIOS revision 02 before they were even released. And so IBM never had that BIOS revision 00 or 01 out there in what's called the wild, or in the world, on the system, because they had already realized a revision 02 or even a revision 03 of the BIOS before they released the system. So they suppressed those earlier versions of BIOS. And I try and find all the BIOS revisions that have been released in the wild to capture the information. And that's the thought. If you have that system, it has an older BIOS, it's a way to upgrade the BIOS and things like that. So then we get into the feature bytes, what IBM called the feature bytes. And we've seen this in the system information tool. The SIT videos I've gone over talks about certain things of the functionality of the systems and what identifies whether that MUL has it or not. And for some of the system information tool, they talk about the SCSI subsystem, whether it's an IML system. If you've watched those videos, and if you haven't, by all means go through and do that at some point after you're through with this video, to see how that information in the system information tool is actually straight from this interrupt 15 hex function C0 hex interrupt call. And we're interested in the last little couple bits, the low order bits of that feature byte 1 in this instance. Bit 1, as we work our way down in that list, bus is microchannel. And then bit 0 is a dual bus system. And IBM meant that for the later things that they had mixed microchannel bus plus ESIA or PCI bus. The system had two different bus types for the adapters that were there. And, I can feature some of those on video later on to show what how those dual bus systems were composed. But in this case, we're just going to focus on whether that, that bit 1 is set or cleared to show whether the system is a microchannel bus. I'm going to move the page as I go through. I kind of want to just show that area is probably real good for just a easy place to leave this page as I go through, and I will link in the page in the video description. But let's go through and get that image back up on the screen of the CheckMCA routine. So at the top you can see I'm going through and I'm clearing the interrupt. I'm making sure that interrupts don't happen for when my routine starts. I don't want the routine to suddenly be preempted by the system to say, hey, I got to do something else, and go through and issue interrupts, having that where the routine could go through and crash the system or something like that. So I'm saying, hey, turn off the interrupts for now. And other than going through and I'm issuing that function call, I'm moving the C0 hex value into that AH register to call the interrupt 15 hex. And I'm going through, and immediately after calling that routine, I move the AL, a 0 value into the AL register. And what I'm doing that for is, if the routine goes through and figures out it's not a microchannel system, I have that 0 in there preloaded in the AL register for the end of the routine for that return value to say, for, that something can examine that AL register to say, hey, it's 0. This is not a microchannel system. So I'm pre-filling that register at the start, the AL register at the start of the routine. So if the call is unsupported, what it does is that's a jump carry. The JC says jump if the carry flag is set, that it's not a microchannel system. And that is basically that the call is unsupported. It's running on that original IBM PC or something else that doesn't support the interrupt 15 hex function C0 hex routine, that interrupt call. So first off, we fail out those very early machines that they don't support the call, so clearly they're not microchannel. And then I go through on the next step is that I set the carry flag. We've already jumped. If the carry flag is set, we've already jumped to the end at the very bottom of things to the trying to find out where can move the text. But anyway, at the bottom I have the it says that's the label for the not MCA, meaning that we're going to jump to that label if we meet the conditions. So as I've got the comment over on the right hand side, whether the call is supported or not. And in those cases, if it's not on a microchannel system, that carry flag is going to be set as a condition of the return values as well. And that's why I'm setting the carry flag manually. Okay, then I'm going through and I'm testing the a particular value in that get configuration table at the point of BX, +5, or the start of that table, the 5th value within that, and that is actually the feature byte 1 location. So we will get that back on screen, and so we're looking at that feature byte 1, and we're looking, hey, does bit 1 have the value of 1? In other words, is the system reporting back that it's a microchannel bus as a response from that interrupt call. And so if it's not set to 1 for that particular bit, then it's not a microchannel system. And the thing is, there is one system that I've recently discovered within the last few days that is falsely reporting some microchannel system when it is not. And that is the model number for that was the 7552. The 7500 series is the industrial PCs that IBM had. And the 7552 is called the Gearbox. It's a basically industrial system, and it is, well, I did a video on it that where it blew a part of the power supply. I was able to go through and pull out all those modules. That's that rack mount unit that was gray, had the gray keyboard. And I pulled out each one of those modules and kind of showed what the contents were inside. The CPU and the BIOS and the numeric coprocessor were in one of those modules, and basically it just has a backplane that you had that device in the rack, and you put in the modules, or you could change the modules around. And there's like 8 modules. I think one is doubled up, the drive module. It's a little bit fatter, a little bit wider than the other modules. And you could have adapters, ISA adapters in some of those slots, and that system falsely reports itself as, and it's based on the 286 CPU, falsely reports it as a microchannel system. Now, the really interesting thing is that the Delmarva machine, that initial system that Chet Heath used at IBM to design microchannel, was based on a 286 CPU and was probably very similar to the industrial, that 7552 system. The 7552, that Gearbox system, was ultimately released later than the Model 50, 50Z, and Model 60. And how do I know that? Well, we'll get through as we look through, as we sort out what machine that we're running on. The Model 50 and 50Z had a BIOS submodel of 04 hex, remember. I've got it right there identified on the page. The Model 60 was the BIOS submodel of 06 hex. The Gearbox at 7552 system, being also based on a 286 CPU, was submodel 06. It had a higher BIOS submodel than the Model 50 and 60, and generally that means it preceded, it was issued after, or released after the Model 50 and Model 60. In some conditions, IBM reused those BIOS submodels, like when they came out with the Model 50Z after they had already released the Model 50, they reused that that BIOS submodel because the 50Z was enough like the Model 50 that they just had it as a BIOS submodel of 04. So that's where we come into a little bit of that, the BIOS model and submodel in this routine of how we can sort through the systems. And so what I initially do, we're at where I have the comment MCA flag bit, I jump out if it doesn't have that bit set. But the next comparison I'm doing is to the BIOS model. And I'm comparing it to, I'm basically inquiring, is it reporting that it's a 386 SX or above? The BIOS model of F8 hex. And if it is, I'm going through and jumping to later routine. I have a virtual guarantee that the system is reporting correctly. It's a microchannel system, and it's based on a 386SX or later on. And as I say, the IBM was the only one that did a 286 based microchannel system, being the Mol 50, 50Z, or Mol 60 are the three 286 based, mols that were microchannel bus. So I'm got rid of the higher CPU levels out of that routine. I'm just interested in focusing in on the 286 models. So that's my next inquiry, and the JE is just jump if it's equal to. In other words, if it matches the condition, jump out of that point in the routine to later on where I have the slots identifier down lower. So it jumps to that label. I'm testing for the BIOS model byte again to sit against FC hex. And so I'm asking, hey, is that BIOS model meaning that it's 286 based? And if it's not, jump if not equal, that J and E to not microchannel, not MCA, label down below, because I know that I'm only looking for the 286. I want to discard all the IBM PC XT, all the PC AT model, because I know that those aren't microchannel, even though they may be, or the XT286. Excuse me, I'm getting rid of the PC XT models and some of the other ones that are the 8088 based or 8086 based units that may somehow, they're lower than the 286 CPU. That 286 CPU is what I'm checking for. And so I know that they're not microchannel. So then the next test I do, that test byte pointer ES BX plus 03, I'm checking against the BIOS submodel in this instance, because if it's higher than the jump above that JE listing, meaning that I'm testing for if it's a Gearbox at 7552 that misreports it's a microchannel system, I want to jump out of the routine because it's not microchannel. I don't want to falsely identify, I want to screen for that system falsely reporting it's a microchannel and get it out of my queries too. So the next step I do is I inquire again to that BIOS submodel, and I'm looking for the whether it is a Model 50 or Model 50Z or Model 60 at this point, or if it's below, like an IBM AT being released earlier before the Model 50 and 60 has a lower BIOS submodel, and saying, hey, if it's below that, the JB, jump or below, if below, it's not microchannel. I'm looking for Model 50s, 50Zs, and Model 60s. Okay, and so I'm going through at that point to clearing the carry flag, in saying up that I know I have a microchannel system after I've sorted out everything else. And I'm going through and I'm actually preloading the value of 4 into the AL register. And that is later on, that's going to be the number of microchannel slots on the system. With this routine, I'm not only interested in if it's a microchannel system, I want to know how many microchannel slots it has on the system, because that's handy to know as well. If it only has 4 microchannel slots, I'm not going to go through in my software and look for an adapter in slot 5. It doesn't exist on that machine. So I need to know how many microchannel slots that has, and they're enumerated as I've explained in previous videos. So I can pick out particular ones in the what slot it's in and things like that. In that extended CMOS we saw where, or even the regular CMOS area, we saw where there's that adapter ID that's put in particular registers for the particular location that the adapter is in. And slot, 1, slot 2, slot 3, different locations in the CMOS space for where those values for that adapter would be at. And the as I explained in that previous video too, the system is retrieving those values as it goes through and runs through the post operation as the system starting up, that running that BIOS code to say, hey, this adapter should be in this slot, checking the adapter ID that's contained in CMOS against the slot to say, hey, is that adapter, is it report the same adapter ID as what I think it is? And if that's true, then it has those POS bytes of how the adapter is configured, stored in later CMOS registers, that it can go through and say to the adapter, okay, here's the configuration that you have on the system. This is how you're supposed to be configured. If it doesn't find the same adapter as what it thinks it's in there, it goes through and issues those, 161 and 163 errors for the configurations change. It doesn't match what the system had in the CMOS settings. It knows that the adapters are wrong. You've added an adapter, you've removed an adapter, that system configuration has changed, so it wants to run the reference diskette. On a microchannel system, the reference diskette. So the Model 50 and Model 50Z, as I went through on recent video, I ran through the Model 50Z, and I was surprised. I ran that system information tool, and it reported 8 microchannel slots. And I said, no, I know that's not true. I know that the 50Z, Model 50Z, only has 4 microchannel slots. Now, the PS2 Model 50 and 50Z were, in their initial releases, they didn't have a extended CMOS area. They just had that regular CMOS area with 4 adapter slots on the systems. IBM didn't need to have any other location in CMOS other than just identifying those 4 locations, those 4 adapters that it was able to do that within the regular CMOS space. So they didn't put an extended CMOS on those systems. Now the extended CMOS area, one of those registers contains the value of the number of microchannel slots that's on the system. The 50 and 50Z don't have that information. They can't retrieve that. So there's no extended CMOS that I can query for the number of slots. So I've hard-coded that it's 4 adapter slots that's on the Model 50 and 50Z is what that means. So I'm stuffing the number, the value of 4 into the L register in the circumstance that I have a Model 50 or 50Z. It's going to identify that way. And I am testing that condition to say, hey, if I have a 50 or 50Z, that BIOS submodel matches 04, I'm going to jump out of the routine. I'm not going to attempt to go further. I'm sure I have a microchannel system, but I'm checking against whether I have an extended CMOS that's used for the microchannel configuration at this point. Let me try and I want to shift this page. Yeah, there we go. Just to get to the bottom of this page a little bit better. And I can shift that back down. Okay, so we have where the only thing that we have left now is the, if it's a 286 system, it's the MOL 60. And the MOL 60 does have that extended CMOS area. In other words, it's going to be able to also report the number of microchannel slots in that particular CMOS register. So all the earlier 386SX plus microchannel units and that MOL 60 are now at this slots label. And I go through and I push the value out of, I'm wanting to read that extended CMOS area. I'm wanting to read a particular register that's the number of microchannel slots. And that location is at 018E hex. And you can see where I'm putting out the high order value out port 75, the low order value, that 8E hex, out to port 74 hex. And then I'm reading the 76, IO port 76 hex for what value it's returning to me. And that's what I'm saying. I want to grab that value for what's in that CMOS register of 018E hex. Give me what the value is at of that register. And so that's what IO port 76 hex is bringing back. And that's the number of microchannel slots. And it's pushed into the AL register. So if earlier I had that value of 4, I run through the routine that it's putting the value of, whatever number of microchannel slots it has in that AL register, and I'm turning back on interrupts. All the systems that are not microchannel have fell to that non-MCA, and of course also the 50 and 50Z fell to that label too. But, we have detected, carry flag is clear. It's a microchannel system. Carry flag is set if it's not a microchannel system. AL register is 0 if it's not a microchannel system. Otherwise, the AL register holds the value of the number of microchannel slots on the system. And CheckMCA, we're doing an in process at the very end of that. So that's the end of the routine. It's returning to whatever called that routine. And we've learned now, that whoever called that routine it can examine the AL register set to say, hey, I know it has this number of microchannel slots, and I know it is a microchannel system. So that's all that routine does, going through. And I'm confident that when we go through the routine, that I've excluded the one system that, and there may be more that falsely claim that they're a microchannel system, handled that condition. I've handled all the conditions. Otherwise, the systems are reporting correctly that they're a microchannel system, and also handled the occasion of what systems do not have the extended CMOS RAM area for that microchannel configuration of the 50 and 50C to hard code the number of microchannel slots that they have. So that's just a look at code. I've known assembly for a long time and use it. This little routine is kind of handy. I do have some other routines that even depend a little bit on this routine of checking the adapter slots for a particular adapter, checking for the planar ID, which is, there are some conditions there, but it's almost always that the planar ID is associated with a microchannel system. So if you're going to call the planar ID function a routine to get the planar ID, you first want to know if it's a microchannel system to where it even has a planar ID at all. So this is kind of a building block of code that I have up. I can cover those other routines at a later point, but this is the CheckMCA, checks if it's a microchannel system, the routine I have up that people can go through and mimic. Now, this is what they consider pseudocode, and I'm trying to write the language and give enough explanation of the routine for what I'm trying to do. But a programmer going through, they got to make sure that the software that they cut, copy, paste, from this routine will work on the system. That they're putting in the right things, of turning off interrupts and going through and handling those housekeeping functions. They're not running this in a condition to where a hardware abstraction layer to the operating system or something else that it will do what it's not intended to do. So use this code at your own risk. I just have it out there. I have it compiled. I'll probably go through it right after this video. I'm going to, the single single quote is actually for a basic programming comment. So I need to change it in there to the semicolon where I have that call supported MCA, the comments that are off in that right-hand column. I need to change that to a semicolon. I mean, even though a programmer knows that that's going to be a comment area. But just to make the routine more complete to being the assembly code it is. So that's a rundown of, I don't know how many bytes this is total. It's not very much. It's not necessarily optimized. I mean, I do just some checks upon that table of what's reported back. But I want code that works. It's fairly self-explanatory, that people can understand. And if there's optimizations of moving bits around or anything else in that, they can do that and optimize the code a little bit more. So if you enjoyed this content, click on that like button. There's going to be a lot more content like this. And by all means, if you haven't subscribed to my channel, subscribe. I want to add on more subscribers and get to the, more viewers that see these videos and everything, and get that notification when I come out with new videos. I want to get up to, goal right now is get up above 1,000 subscribers, and then I can do YouTube announcements. I can announce ahead of time of what, I got a video coming up. This is what I'm working on, whatever. But YouTube, requires you to have more than 1,000 subscribers or more to make YouTube announcements. So let's hit that goal as soon as we can, and so I can be able to do that. But that's all I have for now. This is IBM Museum. Thank you.